Good morning, ladies and gentlemen. My name is Zhang-Kun Wong, and my partner is Harrison Templey. And for this project, we're working under the support of Hexagon metrology. The project we've been working on is optimization of a Cobot loading system. So many of you may not know what Cobot is. Cobot are collector robots, different from industrial robot that you might be familiar with. Cobot can easily meet safety regulations. They don't need a designated working space, so you can work them anywhere you want, and they're easily operable. Therefore, it's cheaper to operate. As of industrial robots are expensive, unsafe, and they require high-skilled workers. And that's the essential motivation for Hexagon to implement the Cobot with their measuring machine. Because of the time and space efficiency, as well as the minimum training required, this project will be overall less expensive. For our best anticipated outcome, we'll have an easily usable software interface that requires minimum training and interaction. Our underlying software will allow users to input files or manual input for package creation. Lastly, but not least, we'll have an overnight runtime capacity that will have the machine operate at off work hours, which is very time efficient. As you can see, this is a picture of our setup right now. This is the robot, and here is our loading system, which contains pallets and parts. The robot will grab part and place it onto the measuring machine for it to measure. For our key accomplishment for this semester, we have manually programmed the robot on a teach pendant. As you can see right here, this is how we've been programming our robot, and this is the first step before we integrate our routine with the database. Once we have integrated our routine with the database, we'll be able to run the routines on files rather than the teach pendant. And this is a significantly faster and easier way for the robot to operate each individual pallet. We have also created a graphic user interface in C#, and this will allow to import JSON files with pallet and part information. We have also created our own data architecture that will allow the robot to know the pick and place location of each individual part. Now I would like to pass to Harrison for more in-depth explanation.
Our first key accomplishment is implementing reverse kinematics software. What is that? Well, in order for a robot to get to a point in space, it first must know its joint angles. In order to find those joint angles, we perform mathematical algorithms in order to find those angles based on a point. This is very difficult since there are many different configurations a robot can take to get to that same point. We implemented software that takes a point in space in reference to a reference plane. This reference plane is very useful, especially when we're working on a drawer of parts. Our next technical accomplishment is our data architecture. Our data architecture is what we use to organize, import, and export data. At the top of our architecture is our drawer. Inside our drawers are two pallets. A pallet is a template in which you store your cell and part data. In the pallets are cells. Cells come in many different shapes and sizes, and there are coordinates on our pallet. Inside those cells are parts, and parts have two different categories of information. We have general and specific. For instance, fan parts, all fan parts are type fan, and they have the same pick location for the robot to pick up, and they have the same cleaning routine. But each specific fan will have its own serial number, its own measurements, and its own status based on those measurements. Our last technical accomplishment is our graphical user interface, or our GUI. The GUI is so that the user can access our data architecture. Right here, you see our part list. You can choose a part, or you can create your own part to put into the cell of our pallet. Once you've filled all the cells of the pallet, you can create your pallet package, which the robot can then use to pick and place parts. Lastly, our remaining challenges for the spring. We will complete a data-driven routine. Currently, we have manually hard-coded the robot to pick and place parts onto the measurement machine, but we'd like to have the robot take the data from our data architecture and automatically get those parts. Next, we'd like to execute a reset routine after an error. Right now, when an error occurs, the robot will stop, and the operator will have to set everything to ground zero, and that's a very tedious and time-consuming operation. So we'd like the robot to set everything to ground zero itself. Next is our QR reader implementation. We'd like to have a QR code initialize all of our information. Instead of a user putting all the information in, we'd like the QR code to be stuck onto the pallet, and then the robot will read that QR code and automatically have that information. We'd like to thank everyone who helped us with this project. Thank you very much.